So this is part 2 of 6.9, line segments in a circle. So here's this part continued. So I stopped right here. We had just shown that triangle ABE was similar to DCE by AA similarity. So now it's asking, let's set up a proportion that compares the line segments. And let's look at just the parts. So let's just go ahead and set up a proportion for all 3 line segments. What's similar to what? So I'm going to use a green highlighter and let's look at this. So by this, AB. So that means I'm going to highlight AB. AB is similar to the first 2 letters here, which is DC. Okay. Let's continue highlighting and then we'll write it out. If I'm looking, the next 2 letters I have BE. Second and third letters BE. Has to be similar to second and third letters CE. So BE has to be similar to CE. Yep. And then let's look at the last 2, which are A to E. The outside has to be similar to the outside, D to E. So A to E has to be similar to D to E. I know it's a lot of crazy colors, but we'll make it. So let's just write this out as a proportion. So I have AB in green. So AB over, what went with AB? DC has to be equal to, that fraction has to be equal to the middle 2, BE over, what were the last 2? CE. And that has to be equal to the outer 2, AE, over the outer 2, DE. So for my triangle, these are my proportional statements. These are how I can find out some side lengths. But we don't always have triangles in circles. What would happen if I only looked at the chords A? So look here. What if I only looked at the chords AC, from A to C, and from B to D? And that's what we're going to do here on this next page. So right before we had these things highlighted, we had, from our similarity statement, if you go back just a second, then we had AE was similar to DE. Okay? And we had that BE was similar to CE. So let's just set that up and see what that looks like. Okay? So if I had AE over DE equals BE over CE. Remember, I'm just saying big to small. These 2 are the smaller ones. See, these 2 are the smaller ones. They're on top. These 2 are the longer ones, and they're on the bottom. So if I knew some numbers here, what would I do to solve this? If I had a number for AE and DE and BE, and I was trying to find CE, remember, anytime we solve a proportion, we are going to cross multiply. So I would take whatever DE is and multiply it by whatever BE is. And that would have to equal whatever AE is times CE. So let's just get specific for a hot second, all right? What if I told you that AE was 3 and DE was 9 and that BE was 5? How could I find CE? X. Well, let's just plug it in how we have it. AE's on top, so 3 over DE's on the bottom. 9 has to equal, little's on top, so 5 over CE I'm trying to find is X. How do I solve this? I cross multiply. So 3 times X is 3X, and that has to equal 9 times 5. So 9 times 5. Well, we all know that 9 times 5 is 45, and that 45 divided by 3, what, if I multiply it by 3, gives me 45, so X is equal to 15. So that's how I can solve it. And guess what? There's a rule for this. So, take just a second to take this in. Would you agree that if 2 chords intersect in the interior of a circle, then So if they intersect, two chords intersect in the interior of a circle, then, so green is my if, or yellow is my if, green's my then the products of the lengths are equal, okay? So just like before, if I were going to set up the proportion above, so I would be, my short lengths are proportional. So CE has to be proportional to BE, and that has to equal, my long lengths are proportional. So AE over BE. And then in order to solve this, I cross multiply. That's why AE times BE has to be equal to CE times ED. And here's a little tip to help you remember. A piece times a piece has to equal a piece times a piece. And that's as hard as it gets for the chord-chord product theorem. So let's look at an example really quick. Not a big deal. Remember, we're always looking along the chords, along a chord. So a piece times a piece. So that means that 15 times x has to equal piece times a piece, 10 times 9. Okay, so 15 times x, everyone knows, is 15x. And 9 times 10 is 90. So when I divide both sides by 15, I get that x is equal to 6. And that's it, guys. That's all we're going to do here. And all we can do from here is just make it a little bit harder. So let's look at this next example. Let me grab my pointer so I can slide over. Remember, we're looking along a chord. So I like to highlight just one chord. I'm multiplying along that straight line. So 8 times x plus 3 has to equal 10 times x. Whoops! Times x. So when I distribute, 8 times x is 8x. 8 times 3 is plus 24, has to equal 10x. That's not really writing very well, but it's okay, 10x. Now, I have to get my x's on one side, so the easiest way to do that is to subtract 8x from both sides. So I'm going to have 24 equals 2x. I divide by 2 on both sides, or what times 2 gives me 24? X has got to be 12. And that's it, guys. I'm finding x. So if x is 12, this is 12. And x plus 3, so 12 plus 3 is this length. It's got to be 15. Okay? So let's look at a little bit more advanced of a problem, and let's review some of those algebra skills. I know it's what everyone hates to hear. So remember, we're going to multiply along a chord. I like to highlight one chord. It reminds me that I'm multiplying in a straight line. So I have 12 times 15 has to equal x plus 8 times x. Uh-oh. Well, 12 times 15 is 180. Well, that's kind of nice. But when I distribute this x times x is x squared, x times 8 is plus 8x. Uh-oh, I've got a nasty little quadratic to deal with. So in order to deal with a quadratic, I have to get everything on one side of the equation. So I'm going to subtract 180 from both sides. And then I'm just going to rewrite this in a way that makes my brain a little bit happier. So x squared plus 80x minus 180 is going to equal 0. And here's where the dreaded F word in math comes from. We have to factor this. Factor. So I got to find two linear statements that when I multiply those together gives me x squared plus 8x minus 180. So I have to look at factors of 180, and I want them to add up to 8, okay? Factors of 180 that add up to 8. Well, the easiest way to do this is to start listing those factors of 180. And unfortunately, there's a whole bunch. I can do 1 times 180. I can do 2 times 90, so on and so forth. But to get to the gist of this, if I were to start thinking about this, eventually listing these factors, I would get to 10 times 18, What happens if I subtract 10 and 18? Well, I either get positive or negative 8. So the only way I can get x squared is to do x times x when I distribute. I know I have to use 10 and 18. Right here is a negative sign, so that means these two signs in the middle, but what goes between x and 10 and what goes between x and 18 have to be opposite signs. That's the only way I can multiply to get a negative. But 8 in the middle is positive, which means that the 18 has to be positive and the 10 has to be negative. Now, in order to solve this, I have to set each of these equal to 0 using the zero product property. So x minus 10 equals 0 and x plus 18 equals 0. When I solve for x on both of these, I get that x equals 10 and x equals negative 18. But wait a minute, is it possible to have a negative 18 length in geometry? Can I have negative 18 feet? Well, if you're guessing, I hope you are, you surely cannot. So your final answer is 10 here. So this side length is 10, and then x plus 8, 10 plus 8 is 18. Okay, so that was how to solve this using some factoring skills. So let's look over here at this problem really quickly. Okay, so I am looking along a chord, multiplying in a straight line. So I have a 9 times 20 has to equal 5x times 9x. Uh-oh, you might be noticing if I can get this 9 to right ever, that's the ugliest 9 I've ever seen, then I'm going to end up with another quadratic. So what is 20 times 9? Well, you guessed it, it's 180 degrees. 5 times 9 is 45. X times x is x squared. Now, this is different from this over here. This is completely different from this because I don't have this middle term, 8x. So when that happens, I'm going to divide by that coefficient. I'm going to get x squared by itself. Well, 180 divided by 45 is 4 equals x squared. Well, what is the inverse operation of squaring? Well, the inverse of adding is subtracting, the inverse of multiplying is dividing, so the inverse of squaring is square rooting. So what times itself gives me 4? X is going to equal 2. So I plug in here, 5 times 2 is 10, and 9 times 2 is 18. Now, the next thing you're going to have is an application problem. I'm going to get you started on this, but I want you guys to try this on your own and be ready to discuss it on Thursday. Notice that it says that 18 inches is not a diameter. So my hint to you is to finish the circle, knowing that it's not a diameter, and let's extend the shape. Now, does this look exactly like we just talked about? So it tells you that from here to here is 18 inches, but don't forget what our congruency marks mean. They mean that it's cutting this into 2 equal pieces. So, if it's cutting those, how can I cut 18 into 2 equal pieces? Then I know that this is 8 and I have to solve for this x. Then the whole length becomes my diameter. Very quickly, do this problem for work this problem. Try it for homework. Okay? Now, very quickly, I want to talk about just a couple other chord facts that you might run into. Okay, and then that's going to be the last part of this video here. So, in a circle, if the radius or the diameter is perpendicular, then the chord is bisected. Bisects the chord. So, E and F bisects EF and EF, the chord. Similarly, if you know that the circle is perpendicular, then you know that the line is a radius or a diameter. So super, super, super quick here. Find the length of NP. Well, this sign here means perpendicular. So, just from what we learned, if this is perpendicular, then it cuts this into 2 equal pieces. If this is 9, then this up here has to be 9, and NP has to equal 18. You guys are awesome. Do practice 9.6 in Canvas.